All right, so we can continue our understanding and utilization of stoichiometry to use the balanced equation to stoichiometrically make calculations about the amounts of reactants or products, or even the elements in those reactants or products. So the stoichiometric statements for something like this equation: nitrogen gas combining with 3 hydrogen gases to form 2 units of NH3. NH3 has a common name. It's called ammonia. All right. It's a product in a window cleaner, and some other cleaners. I think you probably have recognized the smell of ammonia throughout your life for various reasons. It's also a smell that we smell maybe when you have old aged urine, like an old dirty diaper that, not poop, but pee, you get a strong ammonia smell. Okay, so we have many stoichiometric relationships within chemical equations. I can see that for every mole of nitrogen that goes into this reaction, I require 3 moles of hydrogen, and that's a stoichiometric relationship. I can see that for every 3 moles of hydrogen that go in, 2 moles of ammonia come out. Another stoichiometric relationship. You want to do one, Fred?
Okay. If you put 1 and 2 in, you get 2 NH3s.
Very good. That's a 1 to 2 stoichiometric relationship. And there's many others that we can look at. So, how many moles of nitrogen are used when 2.3 moles of ammonia are produced?
Do you just divide it by 2?
Well, that's a good point. That might be the answer, but we always want to use our dimensional analysis to kind of ensure that we can understand what's going on. What goes to the right of our equal sign? What are we looking for?
Moles of nitrogen.
Very good. Moles of nitrogen gas. And we start with what?
2.3 moles of ammonia.
2.3 moles of NH3. And then I go from moles of NH3 to moles of N2. Is that right?
Yeah.
And then I used my stoichiometric information, 1 N2 for every 2 NH3s. And so, yep, you were right. We just divide by 2, and we get the moles of nitrogen gas.
Well, why don't we just divide by 2?
Well, again, the method here allows us to verify we're correct. So at some point, our intuition runs out, and we don't want to rely on our intuition always. Okay? So always use our conversion factors and our dimensional analysis. Okay, if 0.575 moles of carbon dioxide is produced by the combustion of propane, how many moles of oxygen are consumed? There's our balanced equation. What goes to the right of the equal sign?
Moles of oxygen. We want to know how much is consumed.
Very good. Moles of oxygen gas. Okay, and what can we start with?
They tell us moles of carbon dioxide.
Very good. 0.575 moles of carbon dioxide. So, I want to get from moles of carbon dioxide to moles of oxygen. Can I do that? Do we know that relationship?
It's the equation, right?
That's right. The equation tells us that we have what? How many moles of oxygen?
5.
For every, how many?
3.
That's right, 3 moles of carbon dioxide. And again, this is from our stoichiometry, or our coefficients here. 5 of oxygen go in, and 3 of carbon dioxide come out. So I take 0.575 times 5 and divide by 3 to get the moles of oxygen. Good. Okay, how many grams of aluminum oxide are produced when 41.5 grams of aluminum react?
Do we know how to do this one?
Well, we should. I gave you the tools.
You did?
Yeah, it's the same tool. We just use the same tool here, just our equal sign, and use our dimensional analysis and try to work our way through it. And now we have the power of our balanced equation there to help us. Okay? So, let's see. What goes to the right of our equal sign?
Well, we don't know grams of aluminum oxide.
Very good. I'm after grams here of Al2O3. Very good. Now, what am I going to start with?
They'll just say 41.5 grams of aluminum.
Okay, 41.5 grams of aluminum. Whoops, grams of aluminum. And I can go from grams of aluminum to, where do I want to go?
Grams of aluminum oxide?
Well, you could if you know that relationship, but we want to use the power of the equation, right? So we go to the land of the moles. Whoops, moles of aluminum. Then there in the land of the moles, now we're here, we can use the stoichiometry, we can see the moles of aluminum and how it relates to the moles of aluminum oxide. And then we can relate moles of aluminum oxide to grams of aluminum oxide. Okay? What's this one?
I don't know.
You don't know how many grams of aluminum there are per mole?
Oh, yeah, I know that. That's, do you have the periodic table?
I do have the periodic table, but there's some information at the bottom of the slide.
Oh, 26.98.
All right, 26.98 grams for every mole. Now what's here?
I don't know that.
Well, look at it closely. Al2O3, moles of Al2O3, moles of aluminum.
Oh, 1 for every 2 moles of aluminum.
Very good. You see there's 2 moles for every 1 mole of that material. Okay, and then this here?
That's the 101.96.
All right, 101.96 grams for every 1 mole. All right, so our 41.5 divided by the 26.98 divided by 2 times 101.96, and that will give us our grams of aluminum oxide. Okay?
I guess we kind of did know how to do that one.
Yeah, we kind of did, didn't we? I mean, we didn't, but if we just use the method, we gradually can work it out. And maybe after the method, you could say, oh yeah, just divide by grams of aluminum to get it to moles, divide by 2 because 2 moles go into 1 mole of aluminum oxide, and then multiply by the grams to get it back to grams again. But it's not always right in front of you, so your intuition can't always help you that way, right? And frankly, you don't want to necessarily, I wouldn't necessarily feel that you need to do that. This will always tell you that your units work out the right way. So, all right, here's one for you folks at home. You try it, push pause, give it a shot, and then push play, and we'll see what we get. Any ideas?
I think I know this one.
What's the answer?
6.
You think the answer is 6? How did you get 6?
I see that the ratio is 2 to 1. 2 KOH to 1 K2SO4.
All right, very good. So let's see if we can get the same answer with our method here, right? How many moles of KOH are required? KOH are required to make 3 moles of K2SO4. So 3 moles of K2SO4, and I need to go from moles of K2SO4 to moles of KOH. Where do I get this ratio?
From the equation.
That's right. What is it?
2 to 1.
Very good. 2 to 1. So 2 times my 3, that's where I get my 6 from. Excellent work. Okay. How many grams of water will result from the complete reaction of 1.2 grams of H2SO4? Any ideas?
1.2 grams of K2SO4 grams of water be twice as much, so 2.4, I'll guess.
2.4? Okay. So let's see if we're correct. Folks at home, give it a shot before we walk through it. Okay, so what do we want to the right of our equal sign?
Grams of water.
Okay, and what are we going to start with?
Grams of H2SO4.
1.2 grams of H2SO4. Then what?
Go grams to moles.
That's right. How did you know to go to moles?
I don't know. You always go grams to moles.
Okay, we go to moles, SOH2SO4. We go to moles because we want to get the power of the equation. The stoichiometry of the equation can help us when we're in moles, because this is saying 1 mole of this, 2 moles of that, 2 moles of that, 1 mole of that. It's not saying 1 gram of this, 2 grams of that. So I don't think the answer necessarily is going to be 2.4 grams. It might be, but I don't think so, because that's a molar or a mass ratio. We'll find out. Okay, so how many grams of H2SO4 for every mole of H2SO4?
Did they give us that?
That's the 98.08.
Oh, yeah.
98.08 grams per mole. And then I can go from moles of H2SO4 to to moles of water. And then I can go from moles of water to grams of water. 18 grams for every mole, I know that one. What's this molar ratio?
The equation says 2 waters are produced for every 1 mole of H2SO4.
Okay, there we go. So, let's see what we get. We got 1.2 divided by our 98.08 times our 2 times 10, 0.244. Let's see, did I do that right? Oh, no, not times 10. Divided by 10 times 18 at the end there. Okay, 0.44 grams. Okay, very good. So, we see that we have a method that can help us get to the answers if we stick with our method, right? Good place to stop. Next time.